Hello there. What I want to do today is to implement a basic printf function so that we can start doing some more advanced formatting into our kernel code. So if we want to print an integer or a hexadecimal number or a pointer, a string, etc., we can do that without having to call 5 or 6 different functions. Now printf is definitely not a simple function to implement. So I guess we'll start implementing it in here in Ubuntu, and then we will move it to the actual operating system. So we don't have to rebuild the entire kernel and the image and start QEMU every single time to test it. You can run it locally, and once the implementation is stable enough, just copy over the code to the kernel. So let's actually go a new window. Yeah, we're gonna need the terminal right there. So new file. I'll save it to my home. printk, so we don't clash with the libc name. Now for the testing, we're gonna use the function called putchar that simply produces a single character to the standard output. That's going to be then replaced in the kernel with the function that uses the VGA console driver to produce the character. So, I mean, printf is usually defined with something like this, format, and then variadic arguments. Now these are a bit messy to implement, but first of all, right now we really don't care about the count of characters, and we said we're gonna name it printk to avoid clashing. Now variadic arguments, we need standard argument to use, and I have no memory of how they're meant to be used. So let's see. I guess. Sure. Close enough. So let's take this. And so we have a list of arguments, and what's n meant to be? Right, the end of the list. So fmt args and the args. All right, and then we extract arguments using var arg with the type. Cool. God, they could format this code a bit better. So usually what you do is then called I think vs printf, I believe. Let me check that. To string vprintf. Yeah, that one. So vprintf or vprintk format and the argument list. Now vprintk has a v list of arguments. Let's see if this all compiles. Well, of course. So what do we want to do? The objective here is to have a printk function that is able to print character. Let's test that it works before and after the printing. H print a string, hello world. We want to test printing an integer. Do 10, minus 10, 0, next integer. Now I want to do hexadecimals as well. Hexadecimals do not support negatives, if I remember correctly, and I would be surprised if they did. Sure, let's test this as well. 0 hex integer, and yeah, let's do pointers. How do we represent? How do we create a simple pointer? You can do pointer to main is main. All right, and this now, of course, does not print absolutely anything. So printf is essentially running as a state machine. So by default, whatever you get, you print out to the screen immediately. Well, it's buffered usually, but still, a raw character is sent to the screen until we meet a percentage sign. So an escape sequence starts. So first of all, we have to remember whether we are in normal character printing mode or if we are in an escape sequence. So if we meet a C or a D or an S or an X or a P, does that go directly to the screen, or is that just a placeholder for something else? Let's say there's a state and 0 regular and 1 is escape. Now we have to process every character until the end of the string. So if state is 0 and the character is a percentage sign, then we enter the escape state. Otherwise, we just emit the character. Okay, so just like that, we should already get something. Ooh. P. Right, I forgot to increment the pointer. Okay, so everything is getting printed up to the first percentage sign, where we then set the state to 1, and then since we only print if the state is 0, yeah, it just stops there. All right, now for now, let's assume there might be extra states. I genuinely don't know at this point. So if the state is 1, we just met a percentage sign. So I don't want to do super complicated things like zeros and how many spaces you reserve to represent the number. So for now, it's going to be a very simple switch. Thank you. So if you get a C, you do something. If you get an S, do something else. D, X, and P. Right. So, All right, for C, it should be very easy. We just get an argument of type char, and we just emit that right away. Before doing anything else, let's not forget that after completing an escape sequence, we shall reset the state to 0 so that we can go back into regular character printing mode. Sure. Ooh, okay. Was not expecting that. Am I using bar arc correctly? On file. Looks like it. The list and the type. Okay. Sure. Try promote to int when pass to. And that's what you get for ignoring warnings. Okay, so even though we want to extract the char, we will have to extract an int. All right, we're not blowing up anymore, and we're not halting prints because after scanning the escape sequence, we roll back to state 0. So printing resumes from where it was halted. Pretty good. So let's put char this character. There we go. We have our first escape sequence done. Now if it's a string, we just extract that. What am I doing? Now we have a pointer to a string, and now while there's something in a string, we write that and increment the pointer. Working. Okay, now integers, hexadecimals, and pointers. These are going to be a bit more complicated. So first of all, the p specifier automatically prints this. So if you didn't know, the pointer specifier prints in hexadecimal, but also prepends 0x in front of it, which is nice. So now we need a function that will transform a number to a string. So 10 base, 16 base, and 16 base. There's probably str2ull does the inverse, but it's fine. We'll just implement this. And actually, I do have something we can reuse from the previous episode. So you might remember what we implemented puthex. Yeah, we were doing this. So let's move this over and adjust it. So we want a function that returns no, we don't want to allocate any memory. Remember, we don't have a memory manager yet. So end to string, that's gonna do for now. Just an int for types. And we want a buffer. Okay, now instead of writing to the VGA console, we just write back to the buffer. So there's a bit of a name clash here. And same here, so buffer will be equal to the 0 character and return. Let's just be a bit more explicit here. Probably want to do something like unsigned number to string. Yeah, and then have something for just regular signed numbers. So in the way this is going to behave is that if the number is less than 0, we will produce a minus on the buffer, invert the number, and then proceed with unsigned number to string. So the rest is going to be completely identical. Okay, what else? Oh, we need the base, of course. So this function was originally designed for hexadecimal numbers, but in theory, you might be willing to print in base 2 and needing up to 64 digits. So our buffer, first of all, needs to expand to 65 just to have a safe 0 terminator. Probably don't need it, but it's fine regardless. Now, instead of dividing by 16, we divide by, well, not 2, sorry, by the base. And also, yeah, this should be fine. Now, this function breaks if you pass in a base that's less than 2 or greater than 36. But I don't expect anyone to ever be calling this function with that. We will be using asterisks at some point, but we just don't have that yet. I mean, this should be pretty much it. So let's create a buffer, another one. So if you're trying to print a decimal string, decimal formatted number, first of all, we get the number. Now we need something is long enough to accommodate for 64, actually for now 32, but eventually 64 bit numbers in base 10. Grab my calculator. So 2 to the 64th minus 1, 24, 25, let's make it 26, actually 27, because why not? 27 characters. We should probably 0 terminate this. Now this 0 and this 0 are two different zeros. This is the ASCII character for 0 and this is null, so the C strings 0 terminator. Let's do the same here. It's getting a bit messy, but we'll take care of that later. Okay, so No, let's make 32 the super overkill, but never too safe. So number to string n base 10 buff, and now we can just do while buff, put char buff and increment. Right, forgot to pass in the base in here. What? Okay, a bit confused. Value required. Right, we cannot increment this pointer. I'll be too used to pointer arithmetic. Okay, forgot the bracket. Okay. Funny. Okay, something is going really weird with the stack. And I guess this is why I wanted to run this in Ubuntu first, rather than copying to the operating system, because I can now debug what's going on here. How? By actually using the real printf. So what do we get here? Okay, there is a number definitely in n, and it's the one I expected. What's going on here? And this is probably buffer reuse problem. Okay, so n is being passed to number to string. Oh my god. Just need to take this out. Forgot what happens in the non-negative number scenario. Correct. Now hexadecimal. Can pretty much copy paste this. Not a big fan, but it will do. But like this. Oh. A, that's correct. 0 and pointer. Ooh. This is gonna be pointer. And definitely unsigned, and also for the hexadecimal case. We just need to cast, yeah, sure, to a 64-bit type. Pretty good. Wow. That was a bit simpler than expected. But first of all, let's move these buffers out. Have them shared here. Number buffer. Now in theory, since we can produce numbers down to base 2, again we need 65 digits, buffer 65 digits long. Let's replace this buff, number buffer. there is something else I want to implement. So we're going to be mainly working on a 64-bit kernel, but D by default and X only deal with 32-bit values. So if I try to pass something which is 64-bit in size, let's take the largest possible 64-bit value, and let's try to print this. Let's do it both, actually, so we can also test if two escape sequences work in the same string. And move this a bit closer. This has weirdly already worked. I was expecting a failure, or at least a warning. Okay. I should be passing an LL here. I'm sure we will get some problems if I take this to the kernel, but I guess it's time to try. Back. Yeah, let's replace this. Of course, it has to be 42. Right, we didn't include and puthex doesn't exist. That's it. That looks too easy. So let's replace puthex with VGA console puthex. And that's unused, but we don't really care about it right now. There we go. Nice. Let's try the same thing we tried here with a large number. Amazing. Okay. But I'm sure there is a warning if you try to do this in some scenarios. Yeah. I wonder why we get... Let's see if I can get this warning generated for printk as well. Let's actually go and see the documentation. has a print style argument? Well, I guess it's common. Format. String index and first to check. Okay, so if I take this, we'll need to apply this to the header. First to check is 2. Oh my god, this syntax is horrendous. Yeah, sure. Okay, we got the error we wanted, which is kind of good, because otherwise we risk corrupting the stack. Does this work here as well? Yes, okay. So we have to fix this. This makes the parser a bit more complicated, because now after the percentage sign, we are not going to expect a type right away, but we can have modifiers. Now L is not a type in itself, I believe, but we can assume so. So we can say that if we meet an L, we don't produce anything to the standard output, well, to the screen or whatever to put char, but we set a flag that we call no boolean since it is long, defaults to 0. If we meet L, is long becomes 1, and this flag is reset at the end. Okay, so now this will not do anything yet. Set but not used, fine. Okay. So we're resetting the state to 0, even if we meet L. Yeah, this doesn't work. What can we do? Well, we can put. I have a feeling that this is going to grow, like there's going to be more and more flags. So I really don't want to copy paste this into every single case block. So let's have another flag. It's called can reset. So if can reset is 1, then we do effectively reset. Otherwise, we just mention to the parser that there is more to come. Okay. There should be a space in there and a comma. We'll get there. In the meantime, we get to D, and now we can use a 64-bit number, but if the isLong flag is set, then we load long, else, and int. And the same will happen in here, but unsigned. And I guess to be pedantic, warning is gone, and our comma is still missing. Right, because we have to set can reset to 1 for every other specifier. So I guess what we can do is that at the end of the loop, sorry, at the end of the switch statement, if can reset is set to 1, we do reset, otherwise we do set it to 1. So at the following iteration, unless something brings it back to 0, the reset will happen. Yeah, cool. Nothing new in here, it's just this function. Oh. Comment included, yes. And it's coming along, and it will definitely be very useful. And this should be erroring out again. Okay, but we can now pass the L. Very nice. Okay. Well, I guess that is all for now. So see you in the next episode.